Good morning, everyone. Just there is one poll regarding tutorials. So, what time is good for you guys? Friday, 2 to 3 p.m. One vote. Yeah, please vote. Uh, so you make sure that there is no lecture during that time for you, right? So, and actually, during this tutorial, sometime we can also do quiz instead of doing that in the lecture timing. So we can utilize some part of that in quiz and some part in some problem solving, mostly to run by TAs. Okay, so you can vote and let me now start our discussion. So we have been talking about proof techniques from last lecture. So we have seen a couple of techniques yesterday, no, not yesterday, on Friday. Now we are going to see more into it. So this is called universal and existential statements. Let's look into what does it mean. So let's say for any, the theorem says for any odd integer n, there exists, right? There exist integers r and s, where r square minus s square equal to n. Right? So n is odd integer, and your r and s are also integer. So it is not saying that this is true for all integers, but what it is saying that in the space of integers, there exists such integer r and s such that this r square minus s square equal to n, right? So there is a small Slido question. Maybe we can do that first. Let me share my screen. Yeah, so now hope you can see it. So this is regarding the same statement. Oh my god, just a minute. Lecture 5. Yeah. So you can go to slido.com and join P814. P814. I'll wait for some time before you guys join. Okay. So now this is the question. Just 60 seconds. So if n is 39, then what will be the integer r and s such that r square minus s square equal to n? Very simple. If you, because if the options are given, it becomes very simple. You can just try. Okay. Oh, so 20 minus, which one is correct? Both of them are correct. Okay. 69%, 73%, but okay, we can't know. We don't know whether you mark both, but both are both of them are correct. And this is our leaderboard. Okay, thanks. So let's move to our, just to check alertness. Nothing more serious there. Okay. All right. So we have this theorem which says that there exist integers R and S, that means it is not true for any R and S. So how do we prove it? Let's look into. So we can pick any odd integer n, right? Because it is saying for any integer, odd integer n. Right? So that's why we pick any odd integer. So this is very difficult, very different sort of request than what we have seen so far in the last lecture. How on earth do we go about proving something like this, right? So the problem here is, question is there exist, right? So that means it's not like true for everything, but we need to find that such R and S exist, right? In the entire statement. So there are two type of statements, universal and existential. An universal statement is a statement of the form like for all x, some property holds for x, right? For all x, some property holds for x, and like we have seen such a statement so far. Whereas the existential statement is there is some x where some property holds for x, right? So these are the two things, and how do you denote them? So let me write it here. So this is denoted as like for all x, right? For all x, and here there is some x where this is, so this is denoted as there exists x, right? So or if you say there exists an integer, then you write there exists an integer, you write x belongs to g. There exists an integer that holds some property. So now proving an existential statement, over the course of the quarter, we will see several different ways of to prove an existential statement of this form. The simplest approach could be, but that may not always work, is search far and wide, find an x that has the right property, then so that your choice is correct, right? So that's a very simple way to look into this problem. Come back. Let's look into our theorem. So what is it saying? That for any odd integer, there exist integers R and S. So if I have to write in a mathematical notation, I will write there exists R belongs to G and S belongs to G, such that, right, R square minus S square equal to N, right? So this is how I can write it. So we'll pick any odd integer, because for the odd integer there is no constraint on that. For any odd integer, so we can take any of them. Since n is odd, we can write it n equal to 2k, where k is an integer, right? So everyone knows that. So n equal to 2k I can write, 2k plus 1, sorry. So n equal to 2k 1 plus 1, how do we visually interpret this? I have this cell which is over here, which is like 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 and 11. So definitely this is something which is what which is a odd number. It contains 2k plus 1. Like, what is k here, by the way? What is k? Over chat you can reply. 5, right? So 5 is the k, and k plus 1 means it will be like you will have one extra element. So what is this? So what I did is here, all the blue colors shown here, right? So they come up. So what are the blue color cells, or I don't know, this is sky blue. I'm not very good at colors. So, but this colors and the yellow color is that extra element, and all this blue or sky blue is your k, right? So the k and then k plus 1, so 2k plus 1. Now what we are doing is what we have done is additionally we made it k square, right? So this part, if you look into this yellow light yellow part, or this is, so in fact this maybe I can show you guys here, right? So this part I'm talking, this is what, k square. This entire thing is k square. Now what I did is this part, right? So this part I can move this and tile here, right? So this whole part I can tile here. So that becomes this, that becomes this, right? So this is now what is the size of this matrix? Sorry, what is the size of this square? What is the size of this square? Anyone? Yeah, k plus 1 square, right? So the size area of this square is k plus 1 square, right? So if you look into, if I just remove, okay, maybe I will not go to that. K minus k plus 1 square is this. If I remove k square from this square, what will happen? If I remove k square, if I remove k square, oh, sorry, this is a big problem with. Just give me a minute. This is so slides. Oh. Yeah. If I remove k square, that will be, all these things will be removed, right? So if I remove k square means all the whichever marking in red, they will be removed. So what will remain is these guys, right? So maybe I can mark them in green, these guys. And what are those guys? Those guys are actually n, right? Because that's what we assume that is n. So if you remove k plus 1 square k square from k plus 1 square, you remain with some integer n. So that's one way to visualize things, but like this can be a case, right? So k plus 1 square minus k square equal to n. Okay. So that means we can take k plus 1 as r and ks as k, right? So if we do that, r square minus s square is nothing but k plus 1 square, right? So here, k plus 1 square minus k square. And what is k plus 1 square minus k square? That is k square plus 2k plus 1 minus k square, and then you can cut this k square, and that's 2k plus 1. Right? So that's 2k plus 1, and that's it. That's hence proved, right? So we have found such n where this is r square minus s square. In our example, which I just asked, our n was 39, right? So n was 39. So it doesn't mean that there is only one solution, that k plus 1k. You can have many other solutions, but we are not interested in finding all the solution. But what we are interested in is finding one solution. Even if you are, because for proving this, you don't need to find all the solutions. You just need to show, okay, there exists such k where you can really do this, and that k in this particular example was, for example, it was 20 and 19, right? So 20 minus 19, 20 plus 19. Right? This is r minus s, r plus s, and this is 39. But this is not the only solution, right? So the other solution, there was one more correct answer in that, that was at 8 and 5, right? So 8 minus 5, 8 plus 5, r square minus s square is r minus s, r plus s. So this is what, 3 into 13, and this is also 39. So there can be multiple solutions exist, but we are, while proving, we are interested in finding one particular solution, and we can really find like this, right? Okay. So this guys we have done. Now we'll move to some proofs on sets, right? So any questions till this point? Okay. So let's quickly review set theory, what we have seen in the first couple of lectures. That from the last time that we know, right, x belongs to S if x is an element of x does not belong to S, or x is not a member of X if x is not an element of S. This is how we write. S and T are two sets, then we say S is subset of T if the following statement is true: for every object x, if x belongs to S, then x also belongs to T, right? If that is true for all the x, we say that S is subset of T. So here is a theorem. For any set A, B, and C, if A is a subset of B and B is a subset of C, then A is also a subset of C. How do you go about proving this? So this is if P and Q, like just try to like, this is like if P then Q type thing, right? So if something is given and you are interested in finding, proving something. So something, what is given, what is given is A is a subset of B, B is subset of C, that is given to us. But what is we need to prove is A is subset of C. How do you prove? Like we can apply the definition, right? So what definition you can apply? So the definition you can apply is, since you have given, right? So this is given to you, A is a subset of B. That means for all x, right? So I can write now this, for all x, where x belongs to A, if x belongs to A, that means x also belongs to B, right? And since B is a subset of C, that also means if x belongs to B, that means x belongs to C as well, right? So we started with x belongs to A. For all x belongs to A, x also belongs to C. What does it mean? Yes, essentially means that A is a subset of C, right? Pictorially, how do you look into this? So you have A is a subset of B, and B is a subset of C. Therefore, C is A is also a subset of C. Okay. Very simple. Let's look into how this formally it is proved. So let A, B, C be arbitrary sets. A intersection A is a subset of B and B is a subset of C. Since this is arbitrary, we are showing here that regardless of what A, B, C you pick, the result should be true, right? Again, like when if A is a subset of B and B is a subset of C, this means we are actually trying to prove if P then Q. What is P here? These two statements are P, while this one is Q. Right? That's what we are doing. So to do this, we have just taken and for every x, if x belongs to A, then if x belongs to C. That's what we need to prove, right? And that's what we did. Okay. This we have done. And this property is also called a transitivity, right? So transitivity is A is subset of B, B is subset of C, then A is subset of C. This is transitivity. We'll see more into the relationships. Here is a question. But this I will not answer now. You have to think. If I replace this subset relationship with belongs to, right? A belongs to B, B belongs to C, then does A belongs to C? No, not necessarily. Okay, so before we move, there is a very small question again. We will do that first, and then we will. Okay. Hopefully you can see my screen. And again, the same Slido. You need to join is, what is that? Sorry, P814, right? Same P814. This we have already done. We have quickly, if you can join, and we have just very small question. Oh, there is some issue here. I don't know why it's coming like this. The first set is A and the second set is B. Okay, so first set is A equal to 1 and the second set is B equal to this much. 1, 2, 3, 4, 5. Which of the following is true? Okay, let's see. Yeah, so the people are making mistake. So A is member of B, and that is true. But A is A subset of B? Not really, I think, right? So intersection B is phi. That is true. That also seems to be true, no? A intersection B. Yeah, A intersection B is also phi. So there are two correct answers, 1 and 3. Yeah, this is wrong. Yeah, even this should be correct. Anyway, we can. So let me just discuss this again. What is happening here? Yeah, we'll discuss what is a membership thing.
Sir, can you please tell how the first statement was true?
Yeah, I'm coming to that. Right, maybe we can write here. So what was our example? Our example was A was, let's use red color. A was 1, right? So single element. B was 1, 2, right? And then 3, and then 4, 5, and 2 more bracket, right? So this one, right? So this was given, A and B was given, and the statement was set A is a member of set B, right? So what is set A? This guy, right? This is set A. I can always write this as A. So definitely set A is a member of set B, that is true. So I can always write A is a member of B. Right, A is also a member, but the question was set A is a subset of B. Is that true? Set A for A, what does it mean by set A to be subset of B? All elements of A, right, all elements of A should be for any x you take, right? So this is for x belongs to A, for all x should also belongs to B. Right? But is that happening? 1 is not a member of B, right? 1 is not a member of B, therefore set A is not subset of set B. Is that clear? Set A is not subset of set B. Because not 1 is not member of B, right? So that is 1. Now the third question is A intersection B. What is A intersection B? A intersection B, because 1 is not element of A, right? So that is that definitely that A intersection B seems to be pi. Right? So first and third statement was correct. Is there any issue? Questions? Yeah. Intersection is pi. That was marked wrongly in the Slido, but it is correct. A intersection B is pi. Yeah, it is multi-correct. And the second statement is false, right? Anyway, so this is one part, but the question is slightly different, which you can think more, but which is if this instead of this subset, if I replace it with belongs to, what happens? Think about this, and we will discuss that later. Okay. Now we'll see some more on to set inequality and lemmas. So two sets A and B are equal if they have exactly the same elements, right? So if A and B are two sets where A is a subset of B and B is a subset of A, then A equal to B. Right. So our last theorem for the today is this one, which comes to us from the annals of set theory, which says that if A and B are sets and A union B is a subset of A intersection B, then A equal to B. How do you see this as a Venn diagram? Like when you have two sets given and union is subset of, what is it saying? Union is subset of intersection. Right? So this part is your intersection part. A intersection B. How do you move this B, right? This particular B, how do you move so that the union, and what is union? The whole thing, right? So this everything is union. A part, B part, everything is. How do you move this B so that it becomes true? A union B is a subset of A intersection B. How do you move? So you'll move B such that it overlaps everything, right? So if it overlaps, so I will make something like this. This is my A, and my B is also this. If I do that, if they are fully overlap each other, that means my A union B is a subset. Actually, it is equal to A intersection B. In that case, A will be B, right? That's what we are trying to see. So try to imagine this from the Venn diagram. So you have A, what is given to us is A union B is a subset of A intersection B. Right? Union B is a subset of A intersection B. So to make that happen, you need to move B, like this B, you need to move maybe in this direction and make them overlap to each other. And once you overlap, you are done. Right? So then we can say that A and B are equal. Pictorially very clear. But before that, how do you really prove it? Like, let's look into this. So many details, I think that's not required. Skipping that. So Let's look into this particular lemma, where this is a very similar lemma, which is saying that if union is a union of two sets is a subset of intersection of those two sets, then one set S is subset of T. How do you prove? We take any two sets S and T, which is this is given to us S union T. Now we need to prove this. So this is very simple. Let me try to prove it here. So how do you? So this is given to us, right? S union T is a subset of. So we'll take X, right, which is S. Right? Oh, what does it mean? It also means that X belongs to S intersection T, right? Because that's a subset of that. So definitely, if X is in S union T, that means X also belongs to S intersection T. What does it mean? X belongs to S and X belongs to T, right? Because if it belongs to both, then only it will belong to your intersection, right? Now, since S belongs to T, so what is that we are trying to prove here? We have to prove that S is a subset of T, right? How do you prove it? Anyone? How do you proceed?
Sir, we can say that every element of S will also belong to S union T. So every element of S union T is in T. So every element of S is also belonging to T.
Every element of S
Is in S union T, and
yeah.
every element of S union T is in T.
Yes.
Every element of S will be in T.
Yeah. We'll see. So this is how it go by proving. So we start with not with this. So we start with because we need to prove that S is a subset of T, right? So we can start with X belongs to S, and then we have to prove that X also belongs to T, right? If we can prove this, we are done, right? If X belongs to S, that means X also belongs to T. How do you prove it? This is how. So to consider any X which belongs to S, you prove this. So how do you do that? Since X belongs to X, we know that X also belongs to S union T, because if X has to belong to at least one of them, right? And if X belongs to S union T, since S intersection T is a superset of that, so X also has to belong to S intersection T. And since S intersection T it belongs, that means it belongs to S as well as T. That means it belongs to T, and that's what we have to prove. That if you start with X, which is of part which belongs to S, we need to show that it also belongs to T, and that's very trivial to do that, right? Now the thing is, how do you prove that S and T are equal? Anyone from this?
Sir, we have proved that S is subset of T. Similarly, we can prove that T is subset of S. Then only one condition remains, that these are equal.
Right. So how do you prove T equal to T is subset of S? Because these things, right? So S union T, I can always write it T union S. Same thing, right? So S union T, because union and intersections are symmetric in relationships. What I mean is S union T is same as T union S. Similarly, S union intersection T is same as T intersection S. So therefore, if I replace this S to T and T to S, I can come up as a conclusion that T is a subset of S. So from equation 1, we have S is a subset of T. Simply we can say T is also subset of S, and therefore both these sets are equal, right? So that's how we put it. All right. So If yes, yeah, that's all. This is done. So there are a few more things in this slide I can share anyway with this, and you can have a look. But these are something which is not very hard to understand. So, so far what we have seen is what is mathematical proof, what is direct proof, like some examples we have seen for direct proof, and then we have seen some of these inverse, null, and existential statements, and how do you prove in such cases. How do we write proofs about set theories? Or we have seen some of these examples. Next time we will see, like in the next lecture, we will see indirect proofs, which is how do you prove something without actually proving it. Okay, mathematical implication, like we have seen, like what exactly does P and then Q mean. Proof by contrapositive and proof by contradiction. These are some of the very interesting concepts which are used heavily in proof techniques. So we'll see all these in detail in the next lecture. We'll stop today, but we will be covering all these in tomorrow's lecture. Any questions till this point about this course so far? Like any feedback, any question or anything? Feel free to talk. You have a message or talk.
Sir, can you repeat that statement, first statement, how it was correct? A is member of B.
A is in the Slido.
Yes, sir.
Okay. Let's do that here. In a clear page better. Right. So what we had is A is 1, right? And B is 1. Then 2. And then 3. And then 4, 5. Oh, sorry. This one. Right. This is a set in itself. This is set, yeah. Okay, so the question was, first statement was, set A is a member of set B. Isn't that clear? Like, this is set A, right? So set A is definitely a member of set B. But if I write 1, then that means, if I just write 1, that means set A is not like the element of, there is a difference, right? So this is set A. What is your doubt? I mean, maybe, or I'm not understanding perhaps, but it looks very clear. No? Any? Okay, so there are some questions. If A is 5, is that a member? If A is 5, A equal to 5. What do you mean by? No, 5 is not a member, right? So 4, 5, whole thing is a member. Okay, so if the question is, if I have a like this, 5 is not a member, right? So 4, 5 is a member, but not 5. 4, 5 is a member of this set, right? This set is a member of B, not individual 4 and 5, right? So Survi is right there. Yeah, and Vikas as well. Yes. Okay, so the set A is a member of B, set B is a different concept. Now, why A is not a subset of B? Because element of A, right? Why A is not a subset of B? Because you take an element of A. I take, what is the element of A? 1. And ask question like, does B contain 1? B does not contain 1 because B contains set 1, not 1, right? So there is a difference. Okay, so we are starting slightly early today, but we will be discussing more. Element A is not in B. Element of A, yes, correct. Element of A is not in B, yes. Okay, so we will meet tomorrow with more discussions. And if you have more doubts, please feel free to post. Utilize TAs. So we have 4 TAs. You can also directly like email to them with CC to me. Also post in the Google Classroom, and let's have some of these things offline as well. Okay, thanks, and see you tomorrow.